Okay. For today's lecture, let's begin. Today's lecture is about recurrent neural network, or the RNN. Right? RNN is an architecture of the neural network that utilize the output as input. So it means that the thing that is produced as output is used to keep the state of the network, right? In order to make the network able to remember what it has produced before, right? You can, if you learn, if I were to compare this to a more, well, general example, some of you may have known that in computer we have digital circuit, right? And I suppose that you may have seen, well, I would say the basic digital circuit design usually contain the gate, right? Logic gate. And usually when you combine the gate, you got the combinatorial logics. Combinatorial logic is like designed through something like Kano map. That is, you specify input and the output, and then you can figure out what types of digital logic that you need to build. On the other hand, if you want to build a digital circuit that can remember a previous state, then you need to have something like a flip-flop to build a computer to build a logic that can remember previous state, to create something like a clock, something like a digital signal processing device that relying on the previous state. On the same example here, right? If we think about convolutional neural network and the feed-forward network as the combinatorial logic, you can think about the recurrent neural network as the flip-flop, that it is contained a certain way that it is able to remember the previous state of the network. And that is done by feeding the output back through the input, and then use that feedback as part of the input in order to learn how much you want to use from previous state. Before deep learning, there are actually multiple methods that allow you to do so. Right? If you think about time series analysis, time series analysis has a method called ARIMA. Right? ARIMA uses the previous state in order to predict the next state. Right? A model like a sequence model, like hidden Markov model, CRF, use the state of the model in order to make prediction of the next state as well. Or even basic distance or basic calculation in dynamic programming, right? Like discrete time warping. This technique use previous state in order to drive, to accumulate the distance to the next state. Or even if you think further to less machine learning technique, but more of the search technique in AI, you see that the search technique also keep the best so far weight in order to make decision. So it means that memories are important, and incorporating memories into network would allow network to remember what it has performed in the previous step. And we can utilize that in the architecture to allow the system, to allow the network to learn data that comes in sequence, data that relies on the previous steps, and data that have certain inherent patterns that are hidden in the variation of data. Right? So that is the main key concept of this recurrent neural network and the rationale. You want the system, you want the network to learn variations of data that depends on the previous state of the data. Right? If we take a look at the neural network, we can see that there are certain, I would say, modification. There are modifications that you can modify the network so that it could perform differently. For example, in the feed-forward network, when you give the network with a certain input, you can let it produce one set of output, right? This is like you have one-to-one relationship. In this case, you can have the red box here as image, and this can be a class. And the inside here can be a convolutional network, but it still go in the one direction. We would call this as one-to-one relationship between input and output. But the network can have various variations, right? It can have, if the network can contain memories, Then you can have a network that giving it with one input, then it can produce a sequence of output, like in image captioning, that we give in image captioning, that we give the system with one image, and we expect it to generate a sequence of letters, a sequence of words that explain this image. And that is done by having a model that can change state and generate output, change state and generate output, right, multiple times until it reaches the end of sentence. This is an example of one-to-many, but there can be other things as well. Like I can have one here as a word and many here as a speech. Then you have a text-to-speech system that giving the system a text, it can convert that into like pronunciation of the speech. That would be cool, right? Or you can have like a sequence generation, like you have a category or maybe the class here, and then from the class it can generate many output like an image, like or multiple image that explaining the same thing from a class here. So this is one-to-many mapping. Okay, but you need to have a system that can change state in order to change to generate multiple output. The next architecture is many-to-one architecture. That is, you have a sequence of data coming in, and then the model has to again be able to change state in order to receive multiple set of data. And finally, make classification, regression on this data in order to produce one output. An example of this is sentiment classification, that you can feed the network with a sequence of words, and then the architecture, the system would assess this and then produce one output as the sentiment value. Or you can have something like a sequence of image in video, like you can have a video, a multiple key frame from video, then you feed those frame into a model to let it classify the type of scene, or maybe whether it want to detect that there are intruders in the scene or not. This is many-to-one mapping. It can be the text and classify into class as well. It doesn't have to be binary class. It can be multiple types, but this is the say many-to-one mapping. Right. For the many-to-many mapping with a certain misalignment, you can think about this as the machine translation. That is, you have a sequence of text going in, and then you got the sequence of text going out. That means you need to have a model that can act as one part encoder, another part decoder. Okay, in order to encode this into something like a state, and then from the state it can use to generate the translated version in another language. So it means that in order to train this model, you need to have sequence and then another sequence, and then you can train the systems by feeding it into the system, and then the output would start generate as soon as you reach the end of the previous input, right? And lastly, you can have this something like this many-to-many mapping. Like each of these can be a video frame that you want to classify, or it can be something like this is a word, this is a word, and then you predict whether you want to mark it as the boundary or not. Or this is a letter and a letter, and then you predict whether you want to mark it as the word boundary or not in the word segmentation. Okay. So that you can see that there are a lot of applications depending on the architecture, the recurrent architecture that you choose. Okay, now let's take a look at the inside of this architecture, of this blue box here on how does it work. This blue box here receives an input, and once it receives an input, it will produce output. This output will be used to feed as input on the next step. So this can be written as this. You can have this F. F is the activation, like think about it as the function that process the input coming in. This F receives input including the previous state, HT-1. and the input x at the time t. And use these two input and together with theta, which is the model parameters or the weight, in order to compute ht, h at time t, right? So it used the previous state together with the current input to compute ht of the next state. Okay, this is a way that we write earlier, but in fact, if we were to unfolding this repeat pattern, this can be unfolded into something like this one. We have h of the preceding state. H of the preceding state is used to feed the h of, to calculate the h of the t minus 1 state. And this is x of t minus 1. And the results here, ht minus 1, is used to feed as input to ht and xt, right? Computing ht, and then this is used to calculate ht plus 1 together with using xt at time t plus 1, and so on. This is the meaning of unfolding. That means you can have multiple states that is unfolded into steps here. Each of these would pass through the same function. Each of these would pass through the same f. It means that the weight of the network here would contain only one weight in order to transform the ht here into another one here. Okay, so it means that h at time t, comes from this gt of multiple x of the previous x. It comes from the f at time t minus 1 and xt and parameter theta. Parameter theta is quite the same. You will see later on what are the parameter theta for the recurrent neural network model. All right, usually we want to predict a vector at time steps. Some time step, it can be every time step, it can be at the end of the time step, right? So for each of the calculation, we need to process input x at this time step and take in the old state, ht minus 1, and have certain function with parameter w here, certain parameter of the model to calculate the new state. Okay, this function can contain both weight multiplication like what we have earlier in the deep forward network and in the convolutional network, and the activation function afterward. Okay, but in terms of the name, that the name that is defined as recurrent, right, is because you can see that there are certain recurrence here that contains the previous state and then use it to compute the new state. That means the output of the previous step is used in the calculation of the current step. Okay, and please note that here, the same function here, fw, is used at every time step. That means you use the same parameters in order to calculate the change in the state. So we can change the form ht equal fw and ht minus 1 xt to something like this, like below here. This tan h is the squashing function. Actually is the same as it's an activation function, the tan h, and it received the calculation is received from the ht minus 1. Ht minus 1 is projected to or multiply with WHH. WHH has the dimension of h times s. So let me, well, I will just draw it here to show you the dimension of thing that we are talking about here. This is like a square matrix. The size equal of h. So say if ht has the size of k, then this is k by k, and this is 1 times k. And for this one, it would have the dimension equal x and the x and h, right? The dimension would equals x and h. So if x here has the is an input vector with the dimension of 1 time n, right? This is 1 time n. Then the vector here, the weight here would have the dimension of n and k. So after multiplication, you end up with 1 time k, right? So ht here is 1 time k, right? And when this is used to compute output, the ht is multiplied with why, which map from the dimension of h to the dimension of y. Let's say that the y here has the dimension of 1 time m. Then this would have the dimension of m time k and 1 time k. Right. From all this, you can see that the results of multiplication would produce the output at each time step, equaling to the thing that you feed into the model. Okay, this is the thing that is called the vanilla recurrent neural network. That is the neural network without any auto modification. Note that the tanh here, the activation function, can be changed, right? It can be changed to auto activation function that you specify, just like the previous lectures. Tanh has certain property that is, it would have the maximum value of 1, minimum value of -1, just that. But it is still a squashing function. It kind of compressed the range of data into just +1 and -1. All right. This is the vanilla recurrent neural network. When we unfold it here, writing it like this, we feed x, as you can see, we feed x to xt-1 to compute h at t-1 and then get the output by multiplying v here. V is the dimension to get the output here, and then we can compare the output at this time with y to get loss occurring at this time step. Right? So if this is sequence to sequence, we would have loss at each time step. If this is classification and we have loss at the end, then it means that the loss is calculated at the end time step when you finish classification. Okay. Now with this notion, we would have AT, right, an intermediate output equal B, the bias, plus W times HT-1. W is the weight for the hidden state. Okay, wait for the state transition. Right? Think about it as a state transition. Right? Let's name it. I will just name this according to the function. Think about it as the state transition. This is input transformation. And V is the output generation or output transformation. Right? And then you got this multiple, and H is obviously the state. This is input and the output. Right? So this is how it works. And that means need to take in state, compute together with input to produce output. Okay, so the step of calculation would be in this way, that we need to have a certain initial state, H0. Then H0 is used with the weight and X1 to compute H1. This is like the feed forward, right? Compute forward. And for H1 is used as input together with X2 to compute H2. H2 used together with X3 to compute H3 until you have the H and T here at the end. And what you can see here is that W is used repeatedly, right? At every time step, it is shared for the whole calculation here. And let's say if this work is many-to-many mapping, that is each hidden state will produce one output, then we can use this one output to calculate the loss, and we can use the loss to update each state, to update the weight. Combine it as loss and then use it to update the weight. If this is many-to-one, then the final Y will need to be used to calculate the loss here. And then the loss occurring at the end need to be used to update the whole thing before that. If it is one-to-many, again, one is used repeatedly and generate a number of output. The loss for each of these will be used to combine and then update the weight as well. Right. So from this, there are lots of variations of the RNN. This is one of them, the sequence-to-sequence model. So instead of having like many-to-one and one-to-many like this one, this is many-to-many, many-to-one, and one-to-many, which loss can be calculated and used to update the parameters. You can have a sequence like first you feed the model with input but without any output. This is called the encoder. The encoder would take in a number of input, and then the decoder would generate the output. Right? Use the state HT here as the initial state for the next one, and then use the new weight in order to generate the output. This is called the encoder-decoder paradigm, right? That you can use to do the sequence-to-sequence translation. You can do the sequence question and answer. Right? So there are a number of things that can be remembered through this sequence-to-sequence generation. And the loss is calculated here. Right? The losses are calculated at Y here. And you can see that calculated here means that the update of the weight has to go through the decoder first and then the encoder, which create such a problematic design. And that's why there are actually a way to circumvent this, that to help, just like the ResNet, that it create residual in order to make the model able to skip certain step, and the gradient as well to skip certain step to modify the earlier state. Encoder and decoder design, the sequence-to-sequence design also has a certain architecture which is interesting. Right? You can pick those to present in the class, and that would be interesting to see. Now let's take a look at the vanilla RNN. Right, this time. Next time, I just realized that I actually prepared too many topics for the class. We are already at the 10th lectures. Usually we should have about 12, but I prepared something like 15, which are too much. So I'm going to combine some of them. That include the autoencoder and embedding, right? I'm going to combine them to be the concept of the learning representation, which is about autoencoder anyway. We will take a look at that variations with the embedding as an example. And the next time we will take a look at the way that you can create RNN or the LSTM to perform sequence classification, right? This time, let's take a look at the sequence generation. Right. We are going to take a look at the model that is called the character level language model. This is a fun model to learn. Right? You are able to, well, you can create a model that remember pattern, and then it will generate the pattern according to the thing that it remember. Okay. For example, if we were to encode the character hello here as which are the and then we want to encode the hello. Right? We can like get hell here. Then each of these can be used together with the hidden layer to calculate the next layer, and passing through this is the weight, this is the state after multiplications, and then compute the output. And then for this one, we will get like the value that is supposed to be. Like this one, like the next step should be, it actually should be this E. The third one should be L. The next one should be L, and the next one should be O. This is like predicting the next character. Right, predict the next character. So S should follow with E. E should follow with L. L should follow with L. L should follow with O. This is what it is supposed to be in the green. But when we use the input to feed it with the current weight, it produces the results that are not quite so. There are some discrepancy here. This is 4 and rather than high here rather than here. So it means that the network has to adapt according to this example. You got certain loss here. It needs to use this difference in order to update the weight and make it able to learn that. Okay, there is a question coming in from Laxman. Right? When we have backpropagation in self node, will it not cause one line and never ending loop? What is the condition and counter till the time we take the feedback? Oh, let's put it this way. The loss here, right? The loss at the end. When you think about the repeat node, when you think about training the model, I like you to think about the architecture in this manner. That is, the system receives sequence, and then each of these would have the loss, right? It would have its own loss for each of the step, and the loss occurring at the end will need to be used to update the weight at the end and the weight at this step. And the loss occurring here will be used to update the weight at this step and the weight at this step. That means it will not repeat infinitely. Right? It will just be used to update according to the number of steps of the model that it performs, right? So I hope that answers your question. Right? It depends on the number of repetition that the model has to repeat, which usually would be corresponding to input if we talk about many-to-one mapping or many-to-many mapping in this way, or the output if we talk about one-to-many mapping that is supposed to generate. Right, this is language model, right? Let's take a look at this word. The purpose of language model here is to let the model generate text, right? To be able to do so, we will train the model so that when we give it with the one output, it predicts what should be the next output. Like this one, H, it predicts that it should be L, it should be E, and then we can use E and then predict it should be L, L should be L, and L should be O. But initially, if we feed this to the model, we would not get the result like that. We would have certain discrepancy, and these discrepancies, these errors, we would need to be used to update the weight, right? Both WHH, WHY, and WXH. Okay. But you can see the responsibilities here that for the error of O, right? For the error of O, which doesn't contain error. So the last step would not be updated, but the error would be, the error is occurring, this is not no error, occurring here at this step. That means the updating would occur here at this step and again at the beginning, right? Because there are certain, because the last two are correct. Right, but this is the character level language. So for the character level language, we need to train the model so that it can work, it can learn the next character. Then at the testing, when we want to use the model, right, we will feed the model just one character, right, just H here. H is used to generate output layer, and then from the output layer pass through softmax, then we get the result, and then this result is used to feed to the next character, and then use again to predict the next one, and this one is again feed down as input to predict the next one and the next one, right? So that we get the results in sequence. The learning will need to be done through time. That means the loss accumulated through this will need to be used to update back through time here. Sometimes this is too far, especially if your sequence are quite long, and then you want to let it learn the whole corpus. Then it means that the model has to go through like millions of steps, which is actually impossible to learn. So the way that researchers deal with this is to cut it short to get it work something like a truncated version of backpropagation. Basically, you can just creating a sliding window that you say you just monitor this 255 character, and then you can just sliding through the whole text in order to make it learn. Right. So this is the truncated version of the sequence backpropagation. Right, so it means that you may have like you may have to move the windows, right? After calculating this one, doing backpropagation, then you continuing doing the next one, and then backpropagation just at that level. Right, there is this quite cool example of letting the RNN to learn Shakespeare work, and I actually prepared this example for you guys as well in the lab. So initially we have like RNN that cannot generate anything starting from random, and then we train it doing the language model like F followed by R followed by O followed by M followed by the space followed by F. Let it learn this, right? Let it learn this so that it would remember the patterns, not just the recent pattern, but the pattern before it as well, which will be encoded in terms of the state. At the beginning, it wouldn't be able to generate anything. It would look like this one. After you train it more, it will learn something like this is a group of words, right? These are potential words like in, on, a simple word will be learned here. And once you train it more, then it will learn a more complete sentence. And again, finally, it can write something out. Something like this one, which is generated from the model. Okay, so this is how, when you see the paper that tells you that AI can write, AI can do that, and it's based on the sequence generation model, right? So the simplest form would be this, the vanilla RNN. So maybe if your thesis would be in this direction, I don't know, generating some sequence, this would be a cool one to work with. Just let's take a look at this example. The data set that is used to train the model can come from different things. Like this is Shakespeare. You can use something like LaTeX source, the open source for the geometry textbook, and then train it. Actually, the researcher has done it. They use this LaTeX of the linear algebra, and then train the model using the LaTeX, which is a code, then use it to generate a new textbook. And this is the result, which looks, I don't know, it looks legit, but it actually doesn't contain the valid lemma or anything else. You can see that the lemma sequence are correct, assuming 3 and 3, I don't know which trees, but you can see that the notation looks cool. So that means it can at least learn the form of the sequence. You can train it with something like the Linux code, and then it would be able to generate a code out, generate a C code, a certain C code to do something. You can try that, and it would be fun to see what it generates. And then you can see that you can use it to learn lots of things. That is a sequence that depends on the prior sequence. Google has already done that by learning the word that we type onto the search engine, and then let that predict what should be the full sentence. Right? The thing that you will see in the search engine toolbar, the search engine search bar, suggestions come from this model, the sequence model like this one. Okay, you can combine right? Combine the sequence generation with other thing, like instead of starting the state with just the sequence here, you can starting the state with the result of CNN, right? This is the this is image captioning. By plugging in the end of the image classification, say you just remove the, you can just remove the softmax out, and then you get this vector at the end, and then you can feed this vector as input state to the RNN. Right? Let it initialize as RNN, and then train the whole thing together, right? Both language model and image, and then you got the image captioning system. Right. This is convolutional neural net, and this is the recurrent neural net that would generate the sequence. So for this one, CNN would have the same form until this softmax, but let's say we remove the softmax and the final here, but instead we feed it to be the initial state and then use it to compute the next state, and then repeating the generation until it reached the intact. Then you got a system that take in image and then able to produce a sequence of explanation. To do this, you can imagine that you need to have powerful computer, right, to train a model like this one. And also you need to have lots of samples, right, lots of samples, including image data and the sequence data, to be able to pair like this one. Image captioning can generate cool results, like it can tell you that this is dog running on the grass, this is white teddy bear sitting on the grass, but it can be obviously wrong, like this one that is, it tells you that this is the birds perched on the tree branch. The reasons that it gives you this, it doesn't mean that it see the bird, but because the context is similar, this might, usually the image in the data set might contain this branch and the green background and bird. So it would say that this is a bird is perched on the tree branch. This one is a man in a baseball uniform throwing a ball, right? Throwing a ball. Actually, he might be receiving a ball, but because the system doesn't know whether this is throwing or receiving, it will just make this explanation. Or this woman standing on the beach holding surfboard. This is not surfboard, but because the context in the data set might be like this one. At least it can tell that this is woman, and I'm not really sure this is woman or man though. A woman holding a cat in her hand because of the fur, because of the context. A person holding computer mouse on desktop, quite old, right? On the desk, and no computer mouse here. Right, this is the application of vanilla RNN. Let's take a look at how it is done, how the RNN can be performed. I have example here as the implementation of RNN from scratch. I did not use Keras to do the job, but it can be done easily in Keras, just a few lines of code. But let's see how it works here. So here I read the data from the input.txt. Let's see. Input.txt is Shakespeare, right, in text format. I did not share, so should have shared it here. This is Shakespeare in the text format. And we are training the model to capture that. Did I share it correctly? No? Which one? This one. Right. So I read the data in as a text data, and then this first block is just to create the encoding, right? Encode the data to index. And then do the specify the hyperparameter number of the hidden state to 100, and this is the K that I wrote earlier, and the sequence length, say that sequence length should be equal to 25, and the learning rate is 0.1. And initialize the model parameters to a low value. This is wx to h, wh to h, why, and the bias of h and bias of y. This is the loss function which calculate the gradient used to update the parameters. So it take in input and target is supposed to be the edge of the previous state, and then it do the forward pass. Right? Forward pass going forward, right? Going forward, right? Forward pass going step by step. Right? So it use x at each state and then specified as input equal 1 means that we do the one hot encoding, and then pass it to the trans h of the multiplication between xh and x and whh and the previous state, and add with the bias, and then squash it using tan h. You get the state at the current time step, and use it to generate output ys, dot product of the output. And afterward, we use this output to convert to probability of character, and then calculate the log loss of the softmax loss of the character, and then accumulating them. Afterward, we perform the backward pass. The backward pass, this is the initialization of the delta of all the parameters, and then back from the end. And use the difference to summarize all this. So it updated accordingly, use the difference occurring at the end to calculate the gradient that is used to update the earlier state, okay, from the back. And then propagate the gradient back to the previous time step until it reached the beginning. And then we get this dwxh, all of this, right, all of this to be used. And here is the sample function. Sample function job is to sampling because, well, if we were to go back to this one, at each time step, right, at each time step here, it doesn't guarantee that E has to be generated or L has to be generated, right? Because in sequence generation, it can be in many things. You can see that when you type Google and then a keyword, sometimes it generates different output. How does it work in that way, right? It works by sampling. Right? And once you got this distribution, you can use this distribution to obtain what is the likely character at this point by sampling from this empirical distribution, right? Converting this into the CDF and then use it to perform sampling of the output, and you get the sample output from the distribution. Right? The one that has high value will be likely to be sampled. The one that is low value will be unlikely to be sampled. All right. So that is the meaning of sample function here. It take in the for each of the data in range, it would perform random choice of the output according to the probability and give out the output. Okay, lastly, here is the main code. The main code here is initialize everything and then repeat infinite loop. And for each of the step, we would train the model. We would train the model to get the D param and use the D param to update the parameters. And then repeat everything again, perform sample, learning, update the parameter, sample, learning, update the parameter, and then repeat it infinite time. And let's see what happened here. So initially you can see that the sample, this is a sample sequence, doesn't make sense at all, right? But let's wait for maybe 10,000 iterations and see the result. You can see that the loss value reduce, right? Reduce drastically. And now it learned that this language need to have space in order to mark the word. It need to have multiple line, a paragraph. About 5,000 iteration, it learned that it can generate this question mark. It can generate this to mark a type of speaker. After 10,000 iteration, it learned the word I, gate, a lot of late and other thing, right? Right, this is 13,000 learn the word I, in, mood, right? A lot of word, right? Although it doesn't really learn word, although I said it can generate pattern like word, but it doesn't really learn anything about language, right? It just capture the patterns. This is the, I would say, the cool things and the drawback of deep learning. The model doesn't really learn anything. You cannot transfer the thing that it generates here to use with other tasks, but it can capture the pattern. Right? So with certain modification, right, maybe you can utilize this to generate lots of interesting things. Right? But you can see here that with just this simple example, the system can learn to generate a sequence that looks like the book that I opened earlier. It contained here, this is speaker, and the text that is that this person speak. Now it have to like conversation between two characters. Let's wait for a while, say take 10 minutes, right? Let's see how the evolution of the language would come by. Let's take a break. Then we'll come back and then see what we get here. And then we just take a look at another further modification of the RNN. Okay, let's take 10 minutes break, wait for it to learn. All right, let's see how it works so far. Okay, wow, there has been a lot of iteration. Let's skip to the end. So the moment is one, just 100 and just about 150,000 iterations. You can see that it learned the format. The words are still not there, but there are some words that has been learned, like thigh, the, mice, come, the, and a lot of them that are quite already there. I have tried it before. You have to wait for like maybe 1 hour or so, and then it will start to look better. But anyway, right, this is how it is done. Right? We can just leave it at this. Maybe after the end, we come back again and take a look at how it works after maybe million of iterations. All right. Now let's go to what we have left off. At the, oh, sorry. Let's go back a few slides here. So these are examples of the applications. There are a certain modification of RNN to be able to capture different things. The first is some of the patterns doesn't contain just left to right manner. By the left to right manner, I mean that it kind of capture the thing, the preceding context in order to predict the next one. But sometimes the pattern can occur in the opposite way. This is sometimes called the anticipatory effect, right? Like in speech, when you know that you will speak in question style, usually you would have a different intonation when you perform speaking. That is coming from the anticipatory effect in speech, in language, that when people speak, they have certain anticipation of the thing that they will talk about next. So they kind of behaving a certain way in order to reach the next step. This is called anticipatory effect. This anticipatory effect can be captured if you know the end context, and then we can use the end context to predict the earlier one. The anticipatory effect occur in the writing as well, right? When you write, sometimes you know that you will write it this way, and that will make you write it in a certain way, right? So like you knowing the end would go like that, that's why you do a certain action, or like in driving as well. In such a patterns of data, having just RNN would not be suffice. You need to have a certain modification of RNN called the bidirectional RNN. Right? This bidirectional RNN looks just like RNN, but instead of going in just one direction, it has another part that takes the same input, but go from the end to the beginning. And the output is combined from both G and H in order to predict the output, right? So this is bidirectional RNN. I have this paper in 2019 with one of my students. We have this is before politics, all right? So I'm not trying to be controversial here. So we have this word character, and then perform the embedding, and then use this to together with the bidirectional LSTM to predict whether at the end, whether this would be classified as the whether this would be classified as a person or location, right? And we use this to mark whether this should be the name entity or not, right? The name entity of the text or not, by using the bidirectional LSTM together with the embedding, which we'll take a look at how it works next time, right? So that's the bidirectional RNN by having two-way. RNN can be stacked to be multi-layer. So instead of going in just one way, or instead of having just bidirectional, you can have one layer of RNN stacking on top of another layer of RNN, stacking on top of another layer of RNN, right? So to have the deeper model, to be able to remember patterns in multiple layers, okay? So the output is feed as input of the next layer, right? So this is the depth in terms of the deep learning of RNN and changing by time. Or you can have a certain modification of RNN, which is quite powerful, that is called the LSTM, right? LSTM, I will explain it later. There is a better figure to explain this LSTM. But LSTM would have multiple output, multiple logic to remember, multiple gate. Each of these has its own responsibility in the model, right? Let's take a look at it later on when we talk about why do we need LSTM first, okay? So why do we need LSTM? This comes from the paper Learning Long-Term Dependency with Gradient Descent is Difficult in 1994. And on the 2013 papers, right? The vanilla RNN, if we take a look at the gradient flow of the vanilla RNN, you can see that when you compute the forward pass, the output HT is calculated from this W of HT minus 1 and XT, which we can combine, we can rewrite it as this. This is the HT minus 1 and XT, and then multiply with the vector of W HH and W HX. This can be thought altogether as W and the HT minus 1 and XT, right? So this is done by stacking the HT minus 1 and XT together, and then multiply with W, squash it through tan H to get HT. This is the vanilla RNN, okay? Vanilla RNN, when you back propagation one time, it would go back one time like this one. However, when you have a longer sequence, then it need to go from the left-hand side and then go forward. And in the back propagation, you need to go back into the gradient flow each of the step here. The problem is that with this, you can see that W will need to be multiply to the gradient every time that it goes through the block. And that creates two problems. The first problem is called the exploding gradient. Just imagine, suppose you have a long enough sequence and the gradient at the end had to feed back to the beginning. And each step of the calculation need to be multiplied with W. That means if W is more than 1, then you got if the singular value of W, or the volume of W is more than 1, then you got the problem of exploding gradient, because the gradient will be larger and larger and larger, so it will be exploded. In most cases, if the value of W has the value less than 1, you would have the problem of vanishing gradient. That is, the gradient at the end would be reduced step by step. So at the early stage, you see that the gradient would not be exist at all, and that's the problem, because it means that you will get difficult to update the earlier state, or the error occurring at the earlier state. What to do? So the solution for each of that, for the exploding gradient, we can perform something like, this is easy. You can do something like gradient clipping. That is, if it's more than threshold, then you just clip it to the threshold. Or you can do gradient normalization. If it's more than threshold, then multiply with the normalization. For vanishing gradient, we need to change the architecture a bit so that it can accommodate the gradient better. By changing from the left-hand side, that we have the stacking between ht-1 and xt, to the right-hand side, that instead of having just ht-1 and xt passing through tan h, we will now have 4 functions. This input would pass through 4 functions. This 4 function would produce the output called this IFOG, which denotes the rows of each of these. We usually call this the gate. Why is that? Just take a look at the next figure, right? And at each step, these will be used to calculate CT and HT. These CT and HT would carry the state of the network, right? CTs come from the conjugation or the multiplication of I and G, right? I and G. And F from the C at the T-1 or previous state, and F, right? F would decide whether it would let the previous step pass. Right? This is the input and the gate of the input. And HT come from the O and the tan H of CT, the current state. Now let's take a look at how it works here. So the long short-term memory has the notions of these gates. These gates include the first one, the forget gate. Forget gate would determine whether it would erase the cell. If the gate fire up, it would erase the cell. If not, then it would carry over the previous state. So let the cell use the data from the previous state. Input gate would determine whether it would write to the cell. I would use the data, use the input data to write to the cell. Get used determine how much to write. And just like whether you want to open the WAL, how much you want to open, output get determine whether you want to review the data of that cell. So each of these would pass through different functions. FIG pass through sigmoid because these are something like the determination of a percentage to open. And tan H is used to determine the output. The form, O is the output. This is the sigmoid. And G is actually the tan H, determine how much to write. Let's take a look at the form here. This is easier to understand. We have this xt and ht-1 forming the input and the preceding state, or I would say preceding edge state, right? Preceding edge state. These are stacked together, multiplied with the weight. That means the transformation of X would occur at this multiplication. Then the combination here will be used to feed to the gate, right? Multiple gate. Right? This multiple gate means that it will pass through sigmoid, right? Sigmoid, tan H, and sigmoid, right? Think about sigmoid as 0 or 1, or 0% to 100%, right? And the tan H is like -1 or 1, right? So the value can be fluctuated there. To determine whether it would kind of let this to be a positive or negative influence to the output. Okay, let's take a look at the first one first, the forget gate, right? Forget gate would be after multiplication here, it would have a certain output from the multiplication. This output is fed to the activation function F. Activation function F will be used to determine how much of the preceding state, because it used to multiply with the preceding state, how much of the preceding state this cell would allow it to carry over. Okay, so it means that F can block the preceding state. That's why it's called forget gate. It can suppress the memory of the earlier time through this gate. These will be learned by the model automatically though. But you can see that the researcher has to think about the architecture and come up with a way here. I here is I and G. You can see that it goes through different direction and multiply together to combine with C here. Why do you need to go through such things in order to accomplish this? Because this is the path of I and the path of G. Think about I as a switch. Think about G as the learning of the value. So it will learn whether it want to use this input to remember it in long term, right? So it go to upward here, whether you want to remember it in the long term or not. And the get gate here is used to calculate, transform the data from this multiplying with the allowance, the switch, right? And then combine with the preceding state. So if I is 1, meaning that, okay, we will let the CT, the long-term memory, remember this. Right? If I is 0, it means that we will not let this input to be remembered in long term, but we will use it to calculate output through this O. Right? O is used to calculate the output, combining with the current memory, current long-term memory. That is why it is called the long and the short-term memory. Okay. This is the reason of the long-term and the short-term memory. Hence the name LSTM. All right. And the output is calculated through each of the steps. You get HT, then you get output. All right. Okay. So this is how it works in LSTM. The gradient now can flow better because if we want to update the earlier state, then the gradient can be flown to the earlier part, the long-term part. Right? The gradient can flow to the long-term part to update the earlier state. And this creates a better flow in terms of the gradient. And it allows the earlier sequence to be updated. Uninterrupted gradient flow, right? Starting from C3, C2, C1, and C0. There are also other variants of RNN, like the GRU here, which I will not talk about that. But if you want to present that in your research, then presentation, that's fine. I'll try to explain that in a different way than what I have done here. And there are also other types of RNN which utilize in different way. I would encourage you to find different architecture of RNN and then maybe present to your friends. It would be interesting to see how it works there. Okay. These are some of the reference. If you want to perform image captioning, you can try it here. language model and the authors. Right. Let's see what we have for the output of the code. Oh, come on. Still running or no? I think it's hang. All right. So it reached about 250 iterations about here, and got quite better than the beginning. Right? But well, you can see to make it work, you need to train it a lot. And the problem here also about a problem is also that you can see that the sequence is not there because one of the problems is because of the gradient flow. This have a problem with the vanishing gradient, so it will not learn fast, right? This is RNN, okay? Right, this is the end of today's lecture. You also have one assignment on this RNN to write a program that learn the character level data. You can choose any of the text and then train it using the RNN and then determine the result. I will post the instruction to the group later on, but I will just urge you to use the other types of RNN, not the vanilla one. Maybe use LSTM would be better. Where do we post our selected topic? You can, well, once do you mean the paper for the research presentation? All right, right. I will show you here. It's in the Facebook group. Here is the link. Research paper presentation. This contains the document that I opened at the beginning of the class, and also the link which will direct you to the paper reservation slot here, right? Okay, right. Right, so do you have any question about RNN? Today, you can see that application that we learn is the RNN in terms of doing the language generation, predict the next sequence, right? Next time, we will take a look at the RNN again, but in terms of doing data reduction, we will see how we can use RNN to perform prediction of a sequence. Like you have a sequence that you want to map the whole sequence to just one class, performing classification. And that means you can perform regression in the same way as well. Right? We will take a look at how does that work in the next lecture. Okay. Right, we have another question coming in. Right. Yes, I already mentioned at the beginning of the class that I'm going to upload the video tonight. Still, just finish it. Just finished the encoding this morning. So it should take about a few hours to upload and let YouTube do the work. Yeah, I will do that. Presentation is individual work. Right? It's not a group work. You are already master degree level. That means you need to read a lot of paper. Think about this as one of the chance that you kind of doing both work at the same time, where you can enhance your knowledge in computer engineering, selecting one paper out, and then work on it in this class. Right? But the paper has to be about deep learning anyway. If you are interested in other field like in security, in other field, but you can also choose the paper, the deep learning paper that tackle work in that field. But because I bet that there are deep learning paper in every field right now, right? Especially when people talk about application of AI and the use of AI in multiple areas. Deep learning is part of the critical module in that regard. Right? Any more questions? If you want me to take a look at your paper, feel free to send me a link. I will take a look and determine whether it's okay or not. Mostly it should be fine. As long as it does not repeat what have already covered in the class, like it contains, because I would say that what I cover here is like only the basic level of deep learning. There are more advanced version of this, like I'll briefly mention about the attention, about the modification of the model to do different things in the lectures after the next lecture. But there are further modification, right? Like incorporating this with the reinforcement learning, like using something like meta level model, incorporating it to the model itself. Right? So there are quite plenty of them that you can choose from to do in the presentation of the research here. And try to choose one that you are interested in. Maybe it can be one of the paper that you use in your thesis as well. Okay. Anything you like to ask further? Although, well, monitoring, like I'm doing the deep learning work right now, like reading the text and then repeating it and then answer you in speech. Okay, and one other thing that I just noticed in the syllabus is that at first I thought that I would include the use of speech data together with deep learning, but it seems that I don't have enough time because you need to have certain background in speech as well. So we will probably cut that topic off because there are too many topics to cover. So we will end up with about 12 topics at the end, ending with the advanced architecture that we will cover a few advanced architecture. A few advanced architecture means like attention for image. I think the GAN, we will talk about them, right? And then try to implementing those.